In this session, we're going to go over the concepts related to thermodynamics for students taking the A-level chemistry. We're going to go over the lattice energy, the Born-Haber cycle, the enthalpy changes of solution and hydration. We're also going to look at entropy, Gibbs Free Energy, and we're also going to look over the trends in solubility and thermal stability of group 2 compounds like the group 2 nitrates and the carbonates. So let's start with question 1. Use the data in the table below to calculate the value of enthalpy of formation in kilojoules per mole for magnesium fluoride. And we're given this table where we have the enthalpy of atomization for magnesium, the enthalpy of atomization for fluorine, the first ionization energy for magnesium, the second ionization energy. We also have the electron affinity for fluorine, and we also have the lattice energy. Now, this is a classic thermochemistry problem where we have to use Born-Haber cycle to determine the delta H formation. So let's start by constructing a Born-Haber cycle. I've already constructed a Born-Haber cycle over here, but I'm going to do it again, starting by step 1. So step 1, to construct a Born-Haber cycle, first you have to place the ionic solid at the bottom. You can form an ionic solid from the elements in their standard state. Magnesium exists as a solid, and fluorine exists as a gas at standard state conditions. Or you can form the ionic solid through the gaseous ions. So if we have Mg2 plus 2 F minus gas, and this can be formed. The magnesium fluoride can be formed from either the gaseous ions or from the elements in their standard state. So first place the ionic solid at the bottom and write the two ways in which they can be formed. And this is more exothermic. This is why the arrow is going to be longer. And we're going to put it higher. Now we need to connect the two sides together. And in order to connect these two sides, we have to know what are the steps that took place for us to reach this part. And I forgot to write that this is a gas. So first thing we need to do is the enthalpy of atomization. We're going to atomize magnesium. And so magnesium is going to become a gas. And since the enthalpy of atomization, as you can see, it's positive, so the arrow is going to be upward. If it's negative, then it's going to be downward. Now, before I continue, let's first specify each step. What does it refer to? So this is the delta H formation, and this is the delta H of the lattice energy. Now, I'm going to put an arrow upward, and I'm going to put the magnesium gas plus the F2 gas, and this is the enthalpy of atomization of magnesium. And then I have the ionization energy, so I have to remove an electron from magnesium, and this is ionization energy 1. We're going to form Mg plus gas plus F2 gas. Then I have to remove another electron, and this stands for ionization energy 2. We're going to have Mg2 plus gas plus F2 gas. Now this is taking a lot of this page, so let me just make it smaller. And then I'm going to continue. Next, we're going to atomize fluorine. So we're going to form atoms of fluorine. So I'm also going to put an arrow upward because it's an endothermic, and I know that it's endothermic because atomization is an endothermic process, and as you can see in the table that it's a positive, and whenever it's positive, then the arrow is going to be upward. And so this is Mg2 plus gas plus 2F gas, and then I have to add electrons to fluorine, and this is what we call electron affinity for fluorine, which is -328. So we need to put the arrow downward because it's a negative value. And so we have this one where we form the F minus. So this one stands for the delta H atomization of fluorine, and this one stands for the electron affinity of fluorine. Now, a thing that we need to pay attention to is that we're forming 2 moles of fluorine over here and 2 moles of fluoride ions. And the values given here are for 1 mole. They are per mole. So for magnesium, we don't have anything to worry about because we're forming 1 mole. However, for fluorine, we're forming 2 moles of fluorine atoms. And this equation is actually for half a mole of fluorine breaking down to form 1 mole of fluorine gas. This will be the value plus 79. However, over here we're going from F2 and we're forming 2 moles of fluorine. So we need to multiply this by 2. So the delta H atomization over here needs to be multiplied by 2 for fluorine only. So for fluorine, we need to multiply it by 2. Now, the electron affinity. Over here, we have the electron affinity for fluorine, which is F plus electron to form F minus. However, over here, we're forming 2 moles of F minus. So in this case, I also need to multiply it by 2. Now the delta H formation is equal to all of these values. We add them all together and we're going to get the delta H formation. So I have this equation over here and now I need to add the values from the table. The delta H atomization, we get it from the table. It is plus 148 and I'm going to put all of these values. All of these values are from the table. So plus 148 plus 736 plus 1450 plus 79 times 2 because as we said that the atomization need to be multiplied by 2 because we're forming 2 moles of fluorine gas or fluorine atoms I mean. And then we need to add the 2 times the electron affinity, and the electron affinity is minus 328, so it's 2 times minus 328 plus the delta H for the lattice energy, which is plus minus 2958 for the lattice, and we're going to get a value of minus 1122 kilojoules per mole. And this is the final answer. Group 2 carbonates and group 2 nitrates have similar trend when comparing relative thermal stabilities. Drag and drop the below group 2 nitrates to arrange them in increasing order of relative thermal stability. And they said that we need to put the least stable first. Now, thermal stability stands for the resistance of a substance to decompose at high temperature. Now, one thing we need to remember is that thermal stability increases as we go down the group. So since Mg in group 2 is above, then it's going to be the one that's least stable. So if you want to fill this, the first thing we need to put is magnesium nitrate. And then we have calcium because calcium is below magnesium. And then we have strontium, so SrNO3 2. And then we have Ba, barium, which is going to be the most stable. Choose the correct answers to complete the following. The thermal stabilities of the group 2 nitrates, they increase as we go down the group. So we need a higher temperature to decompose the nitrate as we go down the group. And this is because the cation, the radius of the cation becomes larger as we go down. And the smaller the cation, let's say if it was Mg2 plus and Ba2 plus. Ba is further down the group, so Mg2 plus is going to be smaller. And because it's smaller, then it's going to have a higher polarizing power. It's going to easily polarize the nitrate ion, the NO3 minus ion, or the carbonate ion, leading to its decomposition at a lower temperature. Therefore, we need to fill in the blanks. The group 2 cations, they increase in ionic radius as we go down the group. And the smaller the ionic radius of the cation, the better it is at polarizing the nitrate ion. The greater the polarization of the nitrate ion, then the easier it is to thermally decompose. As the polarizing power of the cation increases, the group 2 nitrate is going to thermally decompose easily. The energy cycle involving the enthalpy change of solution of magnesium fluoride is shown below. So here we have the delta H lattice, we have the delta H hydration, and the delta H solution. Now we know that delta H hydration is going this way, so it's going to be equal to the delta H lattice plus the delta H of the solution. So let's just write that delta H hydration is equal to delta H lattice plus the delta H of solution. And you need to memorize this equation. It's better to memorize it. Now, the question was, determine the enthalpy change of solution of magnesium fluoride. They gave us the lattice, and they gave us the enthalpy change of hydration for the cation, the magnesium ion, and the enthalpy change of hydration of the fluoride ion. I need to find the delta H solution. So as we said that we can rearrange the equation to find delta H solution, which is going to be equal to the delta H hydration of both the cation and anion. So you need to remember that delta H hydration should be for the anion plus the cation. So let's first find the delta H hydration. The delta H hydration is going to be equal to the delta H hydration of the magnesium ions, which are 1 mole of magnesium ions, and it's going to be minus 1920. So we're going to put minus 1920, and we're going to add to it the enthalpy change of hydration of the fluoride ions. However, this needs to be multiplied by 2 because we have 2 moles of fluoride ions. So it's going to be plus minus 506 times 2. And the answer for delta H hydration will be minus 2932. Now this value, I'm going to solve it over here. So now we have the delta H solution is going to be equal to minus 2932 minus the delta H lattice energy. And so the lattice energy is minus 2962. So it's going to be minus 2932 plus 2962. And we're going to have a value of plus 30 kilojoules per mole. You just have to know something, that the lattice energy is minus 2962. And because there's a minus over here, so it's going to be plus 2962. And the final answer is going to be plus 30. Drag and drop to arrange the following by increasing order of entropy. Now we know that the gas has the highest entropy because it's the most random state. So it's gas, liquid, and the least random is solid because the solid is arranged neatly and in fixed positions. Now for this question, complete the table below to predict the change in entropy and disorder of the particles of a substance during each of the following changes of states. So let's start with the first one, but before we solve the table, I like to point out what's happening in each process. So melting involves changing from solid to liquid. Here we're going from gas, the condensation from gas to liquid. Freezing, we're going from liquid to solid. And evaporation, we're going from liquid to gas. So the entropy change for the first one is going to be increases because we're going to a more random state, which is the liquid. And liquids are more random than the solid, so the disorder of particles is going, of course, to increase. Then we're going from gas to liquid, so the liquid has less disorder, so it's going to decrease. Gases are more disordered, so this decreases, and the disorder of particles, of course, going to decrease. We're going then from liquid to solid, and the solid has less disorder, so it's the same as above, decreases, and we're going to have disorder is also going to decrease. Now from liquid to gas, the entropy change is going to increase gases are the most random state. They have the highest disorder. So this increases and this also increases. Consider the following reaction that occurs at RTP, which is room temperature and pressure. We have methane reacting with oxygen to give carbon dioxide and water vapor. They said calculate delta G of this reaction, and the unit should be in kilojoules. So the formula for delta G is delta G equal delta H minus T delta S, and the temperature should be in Kelvin. Now, the delta H is minus 802.5 kilojoules, minus the temperature, which at standard conditions, at room temperature and pressure, the temperature is 25 degrees Celsius, which is 298 Kelvin. So we're going to put for the temperature as 298, and the delta S is going to be 201. However, it's going to be 201 times 10 to the power of minus 3, because this is in joules and we need to make it in kilojoules, so you have to divide by 1,000. And so the final answer is going to be equal to minus 862.398. However, they need the answer to three significant figures, so 2, and we have 3, so it's going to be minus 862 kilojoules. Now, choose the correct answer to complete the following sentence. The reaction, since delta G is less than 0, so the reaction is going to be feasible. And since delta G is less than 0, it's negative. And a delta G less than 0 indicate that the reaction will be feasible. Question 6. So we have given the following change at 25 degrees Celsius. We're going from H2O liquid to H2O gas, and the delta H is plus 44, which indicates that it's an endothermic process. Choose the correct answers to complete the following. The entropy change of the system is going to be positive, and this is because we're going from a liquid to a gas, so the delta S is going to be greater than 0 because we're going to a more random state, and this is because evaporation led to a more random state. So there's an increase in entropy. Now select the graph that represents the change in entropy as water evaporates. Now, as water is going from liquid to gas, the entropy is going to increase. So it's definitely not this one. And we need to remember that there will be a very high increase in entropy at the boiling point or at the melting point. And over here, as we can see, that there's no increase. Over here, there's a very large increase, greater than the one that's over here. So this is the correct graph. Now, question 6. The standard entropy change for the system is 119 joules per Kelvin per mole at 25 degrees Celsius. Calculate the entropy change delta S total at 25 degrees Celsius. Now, whenever they ask you about delta S total, there's a formula for it, which is delta S total is equal to the delta S of the system plus the delta S of the surrounding. And we know that the delta S for the system is given is 119, and sometimes they refer to the system as the reaction, so sometimes it's used interchangeably. So it's going to be 119. Now there's a formula to find the delta S for the surrounding, and this formula is delta S surrounding is equal to minus delta H of the reaction, divided of course by the temperature in Kelvin. Now the value for the delta H of the reaction, I think it was given over here. It's plus 44, so this one's going to be minus 44. However, we need to change the unit from kilojoules to joules. So we need to multiply by 10 to the power of 3. So it's going to be minus 44 times 10 to the power of 3 over 298. And we're going to put this value over here. So it's going to be a minus 119 minus 44 times 10 to the power of 3 over 298. And the answer is going to be minus 28.7. And they said find delta S total, so it's going to be minus 28.7 joules per Kelvin per mole. In the next question, they said calculate the minimum temperature T at which the above change would occur spontaneously. Now, it would occur spontaneously when delta G is equal to 0. So delta G is equal to delta H minus T delta S. And if this is 0, then delta H minus T delta S. So T delta S is going to be equal to delta H, which will lead to T equal to the delta H over the delta S. Now, something that students they can make a mistake in is that they might use a different delta S. And the delta S you need to use over here is the delta S of the reaction, which is this one only. You're not going to use the delta S total that you calculated over here. You're going to use this delta S, the delta S of the system. So the temperature is going to be equal to delta H over delta S. Delta H is 44 kilojoules. However, I'm going to change it to joules, so it's going to be 44,000. So I multiplied it by 10 to the power of 3, and I divide by delta S of the system of the reaction, which is 119, and we're going to get a value of 369.74. However, they needed to 3 significant figures, so I'm going to round it, and it's going to be 370 Kelvin. So this answer is going to be 370 Kelvin. At 373 Kelvin, water and water vapor are in equilibrium. Choose the value of the overall entropy change at equilibrium. And they're asking over here about delta S total, not the delta S of the system. So at equilibrium, delta S total is equal to 0. This is something that you need to know. And this is because at equilibrium, no further spontaneous change is going to happen. The next question, calculate the entropy change of the system, delta S system at 373 Kelvin, and give your answer to 3 significant figures. Now, delta S total is equal to 0, but delta S of the system is not equal to 0. Something else is equal to 0, and it's delta G. So delta G is equal to delta H minus T delta S. At equilibrium, delta G is going to be equal to 0. Delta H is going to be plus 40.6. Let's just rearrange the equation. So we need to find delta S. And so delta S is going to be equal to delta H over the temperature. And the delta H is 40.6 times 10 to the power of 3. I will change it to joules. So I have to multiply by 10 to the power of 3. And I'm going to divide by the temperature, which is 373 Kelvin. Now, the value that I'm going to get, if I divide these, I'm going to get a value of 108.84. And I'm going to round it to 3 significant figures, so it's going to be equal to 109. So the final answer is 109 joules per Kelvin per mole. CaCO3 is the most common mineral in Earth's crust. Write an equation to represent thermal decomposition of CaCO3. Now, when calcium carbonate decomposed, CaCO3 solid is going to become calcium oxide solid plus CO2 gas. Why does the decomposition of CaCO3 need heating at a high temperature? Now, the first option was it's an exothermic reaction. This is false. This is an endothermic. It has a low activation energy. If it needs a high temperature, then it needs a high activation energy. So this is also false. It is an endothermic reaction. This is correct. It releases heat. This is false. It requires heat, actually, because it's an endothermic reaction. So the only correct option is that it's an endothermic reaction. Now, then the next question, they said, choose the carbonate that decomposes at a lower temperature compared to CaCO3. Now, a carbonate that decomposes at a lower temperature, this means that it should be in group 2 and it should be above Ca, and the only element is Mg is actually one of the elements that is above Ca. So the carbonate is going to be MgCO3. Which of the following statements explain your choice in part C? So we chose Mg, and it's because it's the one that's above Ca, and it's because it has the smallest ionic radius and has the highest polarizing power. So this is the correct option. And you need to remember that for group 2 nitrates and group 2 carbonates, that as we go down, the thermal stability is going to increase. Now, question 8, we are given the standard entropies of the 3 species are given in this table. And the question was, calculate delta S for the reaction to H2O liquid gives 2H2 gas plus O2 gas. Now, to solve this question, we need to use the formula, which is delta S for the system is equal to the sum of N product, the entropy of the product, minus sum of the entropy of the reactant. And remember that N is the coefficient. Now, the coefficient for the products, we have 2, and for the H2, so it's going to be 131 times 2, and we're going to add to it 205, and we're going to subtract them from the H2O, which has a coefficient of 2, so it's going to be plus 70 times 2. So if we're going to include this in the equation, it's going to be equal to 2 times 131 plus 205 minus 2 times 70. It's going to be equal to plus 327 joules per Kelvin per mole. So this is the answer. It's plus 327. Now, in the next question, they said delta H for the reaction is plus 572. Calculate delta G for the reaction. Now, the formula for delta G is equal to delta H minus T delta S. And the delta H is 572 minus the temperature, since we're talking about standard conditions, it's 298, so minus 298, and the delta S is 327, so it's going to be 327. However, we need to change it to kilojoules, or we can change this to joules, but because they need the answer in kilojoules, so I'm going to change the delta S to kilojoules, and I'm going to find the answer, which is going to be equal to 475 kilojoules. So it's going to be equal to plus 475 kilojoules per mole. Now, in the next question, they said, choose the correct answer to complete the following sentence. As the temperature increases, the spontaneity of the reaction, and we need to complete this. So the equation for delta G is equal to delta H minus T delta S. And the value for delta H is actually a positive value. So this is a positive value. And the delta S is also a positive value. Now, if the temperature is going to increase, so T delta S is going to increase. And this means that the delta G is going to become less positive, or it's going to become more negative. And if delta G decreases, then the spontaneity of the reaction is going to increase. And this is because a reaction is spontaneous when delta G is less than 0. So as the temperature and delta S increase, and we're subtracting from a larger number, delta G is going to decrease mathematically, and we're going to talk about a more spontaneous reaction. The spontaneity of the reaction is going to increase. Salts in their hydrated form contain water molecules embedded in their crystalline structure. The enthalpy of hydration of such salt is very difficult to measure. Chemists calculate the enthalpy of hydration of these salts using an enthalpy cycle of hydration. Diagram below represents the enthalpy cycle for hydration of sodium thiosulfate. And the question was, calculate the enthalpy of hydration of anhydrous sodium thiosulfate. Now, anhydrous, this means that doesn't contain any water. And we're given the enthalpy of solution of anhydrous sodium thiosulfate and hydrated sodium thiosulfate, and they're minus 7.6 and plus 47.4 respectively. and we need to find delta H hydration. So this diagram is not very clear. Here we have a delta H1, here we have delta H hydration, and here we have delta H2. And since we're going this way, actually going from this arrow over here, so this means that delta H1 is equal to this value plus this value. So I'm going to write that delta H1 is equal to the delta H hydration plus the delta H2. So I need to find the delta H hydration. So delta H hydration, by rearranging the equation, is going to be equal to delta H1 minus delta H2. So let's look at delta H1 and delta H2, and we just have to substitute them from the values that we are given. So they gave me the enthalpy of solution of anhydrous and dehydrated. So the anhydrous one is minus 7.6. And delta H1 represents the anhydrous one because we have sodium thiosulfate without any water molecule. We're adding water to it, and now it's becoming hydrated. So delta H1 is for the minus 7.6 minus the delta H2 is for the hydrated one, and the hydrated one is this one as it has water molecules in it. So it's going to be minus 47.4. So it's going to be actually minus 47.4, and the value is minus 55. And they need the answer to 3 significant figures, so I'm going to put minus 55.0 kilojoules per mole. Question 10. The following table lists some enthalpy changes. I have the delta H formation of MgCl2 solid, the delta H formation of MgCl2 aqueous, the lattice energy, and the delta H hydration of Cl-. They said write the equation of the enthalpy change of solution. Now the enthalpy change of the solution, it's where I'm going from the solid to the aqueous part. So I have MgCl2, and it's a solid. I'm actually adding water, and I'm going to form Mg2 plus aqueous plus the 2Cl minus aqueous. So whenever they say solution, enthalpy change of solid, it's where I'm going from the solid to form the aqueous ions. Use the given data to calculate the enthalpy change of solution of MgCl2 and give your answer to 3 significant figures. Delta H solution of MgCl2. Now for the delta H solution, I'm going from solid to aqueous, and I have to use this table. So to find the delta H solution, I'm going to use delta H formation. It's as if I'm saying products minus reactants of aqueous minus the delta H formation of solid, and it's going to be minus 801 for the aqueous one, and then it's minus 641. I have to subtract, and the value is going to be minus 160, and so I have to put minus 160 kilojoules per mole. Now in part C, they said use the given data to calculate the enthalpy change of hydration of Mg2+. So, and I have to give your answer to 4 significant figures. So I have to find delta H hydration of Mg2+. Now the formula for delta H hydration is equal to the delta H lattice plus delta H of solution. Now the solution we got it before in this part, and it was minus 160. So I'm going to put minus 160. And for the lattice, it's over here. It is minus 2526. And we need to get the delta H hydration. And so it's going to be equal to minus 2686. Now this is the delta H hydration. However, I have to find the delta H hydration of Mg2+. So to find the delta H hydration of Mg2+, we know that delta H hydration is equal to the delta H hydration of Mg2 plus 2 times the delta H hydration of Cl minus, because we're talking about MgCl2. So we have Mg2 plus and we have 2 Cl minus. So this delta H hydration needs to be multiplied by 2. So let's erase this part. So the delta H hydration is, let's solve this one over here. I'm going to substitute the values. Delta H hydration is minus 2686. Delta H hydration for Mg2 plus is the one that I need to find. And the 2 times the delta H hydration of Cl minus is going to be plus minus 796. And so the delta H hydration for Mg2 plus is going to be equal to minus 1890. So this value is going to be minus 1890. Question 11, the standard enthalpy of atomization is always positive. Fill in the blanks with an integer. The symbol in delta H represents the condition of the reaction, and we need to memorize this symbol. We're talking about standard conditions, so it's actually 101 kilopascal and a temperature of 298 Kelvin or 25 degrees Celsius. What is the definition of the standard enthalpy of atomization? Now, atomization, it's where I'm forming a gaseous atom. So it's not when 1 mole of ionic compound forms, not their molecular compound forms. It's actually when 1 mole of gaseous atom is formed and not aqueous ion. So the only option that's correct is this one. They said then choose the correct answer to complete the following sentence. And delta H atomization is always positive, and this is because the bonds are broken. And because we're breaking bonds, so this leads to a positive delta H atomization. We need energy. In the next question, they said, write the equation that represents the enthalpy change of atomization of lithium. Now we need to atomize lithium. So lithium is a solid, and by atomization, we're making it a gas. And this is the equation. Question 12, the table below contains entropy values for some elements and compounds. Choose the correct answer to complete the following. Solids have lower entropies than liquids and gases because their particles are actually arranged neatly. So because their particles are regularly arranged. Calcium oxide, which is CaO, has lower entropy than calcium carbonate. Lower entropy, we mean lower disorder, because it has. So CaCO3 has more particles, CaO has less particles. This is why it has a lower entropy. So it's because it has less number of particles. Now, substances of perfect crystals have entropy of 0 at a temperature of 0 Kelvin. And this is the third law of thermodynamics, which you need to know. Which of the following conditions indicate that a reaction is feasible? Select all that apply. Now, a reaction is feasible when delta G is negative, so it's when delta G is less than 0, and when delta S total is greater than 0. We have a positive change in the entropy, and delta G is less than 0. So it's delta G is negative. Now, the next question, nitrogen gas reacts with hydrogen gas to form ammonia as shown in the following chemical equation, and they gave me the value of delta H. And they said use the data in the table above to calculate the standard entropy change for this reaction. So we need to find the delta S reaction and give your answer to 3 significant figures. So this is the reaction, and I have to go back to the table. So in this table, I have NH3, which is 192.8, and I have the N2, which is 191.6, and I have H2, which is 130.6. So the formula that I need to use is delta S of the reaction is the sum of N products minus the sum of N of entropy of the reactants. Now NH3 doesn't have any coefficients, so I'm just going to put its value from the table, 192.8 minus The coefficient for H2 is 3 over 2, so I have to put 3 over 2 multiplied by 130.6. I have to add it to the half and 2, which is plus half times 191.6. As you can see, all of these values I've used from the table. And then the delta S is going to be minus 98.1. So the delta S for the reaction is going to be minus 98.9. In the next question, they said, calculate the minimum temperature T above which this reaction is going to be feasible. So to find the temperature, the minimum temperature for this reaction to be feasible, we have to use this formula, T equal delta H over delta S. And remember, we know that we need to use this formula because delta G equal to 0. We put delta G equal to 0, and we will find that delta H is equal, by rearranging the equation, is equal to T delta S. Now, delta H is minus 46.0, and it's given over here, so I will put minus 46 times 10 to the power of 3 because I will change it to joules, so I have to multiply. Be careful from the units. You should make sure that the units match, and I'm going to put the delta S, which I found earlier, which is minus 98.9, and so the value is going to be equal to 465. So I'm going to put 465 Kelvin.